Okay.
Hi, good morning, good afternoon, good evening, everyone. Welcome to the Geoscience and Geoenergy webinar of 29th of April 2021. Sebastian and myself are delighted, pleased, and honored to host our dear colleague Maja Rücker from the University of Eindhoven today with us to give a lecture. And she's our special, also distinguished guest for a reason that all young audience of us know. She's a co-founder of the Porous Media Tea Time Talk series as well. So we are doubly grateful and delighted to host her today with us. Maja is assistant professor in the Energy Technology Group within the Mechanical Engineering Department at the University of Eindhoven, Technical University of Eindhoven, which is TUE, we call it. There are two technical universities, by the way, in Netherlands. Technical University, or not more than that, Technical University of Delft and Eindhoven. Eindhoven is TUE. So Maja is coming from that city of Eindhoven. Between 2019 and 20, she worked as a postdoc researcher in the Chemical Engineering Department at Imperial College London. She received her PhD in Petroleum Engineering in a joint project of the Rock and Fluid Physics team at Shell Global Solutions International and Imperial College London. She also holds a BSc and MSc degree in geoscience from the Johannes Gutenberg University in Mainz in Germany. Maja is the Interpol Poor Lab Award winner in 2021. It's a prestigious award offered to her this year, and it's really and well-deserved. And also, as I said at the beginning, she's co-founder of the very impactful, contributive, and quite motivational initiative, which is an online webinar series called Porous Media Tea Time Talks. And we always have been motivating our audiences to subscribe and follow their channel, as well as also volunteer to give a presentation and talk as well. That channel provides young researchers with a platform to share their knowledge, science, research, and also challenges, and also seek for broadening the network, which is quite important and crucial in their development of their professional career. Please do visit Maja's research outcome in her Google Scholar page. She's quite an active scientist and researcher in the porous media diverse applications, mainly on the fundamental physics of multiphase flow in porous media across scales. It's a pleasure and honor to host you, Maja, today with us. And to the audience, please note Maja's lecture would last for about 30 minutes, like always. And after that, we will host the session as a discussion session, question and answering. Sebastian will chair the discussion session, as always. And please do type your questions anytime you feel appropriate. They may trigger other questions by the audience as well. And so please do not wait till the end of the lecture. You would not disturb anyone, but just motivate others to contribute and ask questions. And please, lastly, also mentioning Maja has recently got the appointment at the University of Eindhoven. So she's been there since November last year. Please do contact her after the talk if you see that the research topics, everything else is interesting to you. Get in touch for collaboration, for questions, for networking and everything. So without any further ado, Maja, the stage bandwidth, everything is all yours, and we are looking very much forward to hearing your lecture today.
Thank you very much for the introduction, Hadi. I'm a big fan of the Geoscience Geoenergy webinar since the beginning. In fact, it was an inspiration for us to start the Porous Media Tea Time Talks. So I'm very delighted to have been invited to present here. I also would like to say hello to the audience. Thank you for tuning in. I'm happy now to take you on a journey through the length scales in subsurface reservoirs, from molecular interactions to Darcy scale flow behavior. This work has been done in collaboration with various people listed here on the slide. In particular, I would like to mention the Imperial College Shell Digital Rock Group, where most of the research was conducted. Oops, it doesn't want to switch. One moment, please. Okay, now we can start. So when we talk about subsurface applications, we usually talk about flow in porous rocks and in porous reservoirs, and we usually monitor and assess our reservoirs looking at a geological model in which we divide our reservoir into grids, and each grid gets assigned properties. And I think in one of the first presentations, Martin Blunt mentioned that these properties are rather difficult to obtain. I think, companies spend billions to characterize the rocks for the geological models, and usually the quality of the measurement is actually rather poor. So there is an interest and there is a lot of effort put into understanding how these properties relate to the rock, and how they can be determined in other ways than conventionally done. And in this work, which I present today, I basically will mainly talk about flow properties and their relation to the mineralogy and geochemistry of the rock. When we talk about flow in porous media, the simplest first step will be to think about single-phase flow. So this is usually measured, or we characterize it with permeability, which is the ability of the rock to transmit fluid. And we usually use, it's described through Darcy's law, the equation here. Now, often in our reservoirs, we are looking into a multiphase flow phenomena. So we're trying to retrieve some of the fluids inside the rock, and we usually do it by replacing it with another. And then we have multiphase flow. So we have multiple fluids within the rock at the same time. And then we use a mineralogical extension from single-phase flow to two-phase flow, or to multiphase flow. We are talking then about relative permeability, which is the relative contribution of one fluid compared to the overall permeability of the rock. Now, the relative permeability will, of course, depend on the amount of one liquid compared to the other inside the rock. So it's a function of saturation or water fraction, as you see here. Now, how exactly the relative permeability saturation relationships look like? They depend on the various characteristics, in particular the interaction of the fluids with the fluid and with the solid. We call it wettability. So here you see this relative permeability saturation relationships for water-wet rock, which means the rock prefers to have water inside. Here you see the relative permeability of the oil-wet rock, which means basically if you want to produce oil, so this is an example given for an oil reservoir. So if you want to produce oil, the oil actually sticks to the surface of the rock and therefore changes the shape of the relative permeability saturation relationship. And here you have a mixed wet state. So parts of the rock are water wet, parts of the rock are oil wet, and this is of course also influencing the way our fluids flow through the porous rock, and therefore makes a change in the relative permeability saturation relationship. But when we think about wettability conceptually, we usually think about what happens at the molecular scale. So this is the interaction between the molecular interaction between the molecules of one fluid and the molecules of the other fluid, and with the surface of the rock. And this is this molecular interactions between all those phases, they can be transmitted into an intrinsic contact angle. But this is not enough to actually really directly state of what will happen at the core scale. Yeah, so just having this measurement at the molecular scale, knowing the interactions, do not, at the current state, do not lead us to determine what happens at the core scale. And the reason is all these steps which are actually in between. Yeah? So mechanisms which are occurring at the subpore scale and mechanisms which are occurring at the pore scale. Some of you may be a bit familiar already with this slide. It was actually, I think, a very similar one was presented by Ryan in his presentation, where he talked about how to upscale vertability using the Minkowski functionals. In this presentation, I will look out at the vertability across length scales more from an experimental side. I will show you a few different experiments which we did, which basically show the effect of the different length scales on the core scale responses. So this graph will join us for the whole session, will join us on the journey, and you can actually, you will see it, I will switch to the next slide already, you can see it actually here on the right-hand side. So if you ever get lost across length scales, just look at the top and you will see where we currently are. So going back, yeah, we are going through a journey across length scales from the molecular scale to the core scale. And I would like to take one of the conclusions, mention one of the conclusions of the investigations right now. Something which we didn't know. So I mentioned that all these aspects influence the core scale behavior. And what we basically did is we not with the aim to do that, but we basically fixed the molecular scale. So we used same crude oil brine rock systems to compare different flow behavior at the core scale. And only by accident, we actually noticed quite some different behavior at the core scale. Yeah. So here we had, as I stated, the same crude, the same brine, and this is cation rock. So for both cases, we wanted to compare spontaneous inhibition at the largest scale. So this is a Darcy scale sample plug, 1 inch in diameter, I think 10 centimeters in length, and a micro CT plug. So we wanted to see the overall behavior during spontaneous inhibition and compare it with dynamics, which we observe at the smaller scale with a micro CT. And we treated the we injected water, then we injected oil, and then we put it into the amode cell vessels. So these are vessels filled with brine, where the oil can spontaneously, the water can spontaneously imbibe, and the oil gets produced. And then we noticed that the wetting behavior was actually quite different. So you see here the oil which is emerging from the rock is clearly showing an all wet behavior. So it's actually sticking to it. It wouldn't flow away even though the volume is sufficient large to get produced. When we look at the smallest sample, we actually saw a lot of oil being produced, and the drops which were emerging out of the rock showed a clearly water wet behavior. Now, there was a slight difference in the way we treated the two samples. For the larger scale, we used the centrifuge. So we centrifuged the sample shown here. So it was filled with brine, then with oil. Then as we rotated, capillary pressure applied and pushed the oil into the sample. And in the second case, we flooded the plug. So it was filled with brine first, and then we started injecting from the bottom in the flow cell. And a slight difference, the slight difference is basically the absolute capillary pressure which we applied at the end. Yeah, because we control the capillary pressure with the centrifuge, we could go to much smaller, we could enter much smaller pores than with the flooded sample. Yeah? So in case of the flooding, we didn't use a porous disc, so the rock was limiting itself when it came to filling it in. So only the larger pools were basically filled, and we guess that somewhere here in between there seems to be a difference in why the wetting response is such in one case and so different in the other case. Now, what I would like to highlight here is that in between those two, we actually do not have many pores. In fact, it's really just a few. You see it also here in the capillary pressure saturation relationship. So we increase the capillary pressure, but actually the saturation doesn't change that much anymore. Yeah. So there are not many pores, yet we wanted to investigate the reason. So we started looking into that with microcomputer tomography. So you see in particular here, what happens, the amount which has got flooded, we actually expect to still see some of the two fluids, the presence of the two fluids, to be able to distinguish between what happened. Yeah. So these are two micro-CT experiments. We used a different crude here than before, but these two experiments, the one which was conducted, the micro-CT measurement, which was flooded, and the micro-CT measurement, which was centrifuged, were both where we still had consistency with the same. So we used the same crude for these two experiments. The rock is again Ketten limestone, and we use also the same brine as before. And you see in both cases you see water and oil. So here the bright phase is the water phase, the dark phase is the oil phase, and you see that that both is present. So this is after. So we initialized the samples, we water flooded the samples again. So this is at the end of the. So when you think about well pump, it's at the end point after the water flood. Yeah? So you see here everywhere water, and in both cases you see some oil films remaining, though the extent of the oil films in the bottom image is actually much larger. So you really see a continuous film covering everything almost. But more convincing about the wetting state are actually the contact angle measurements. So the contact angle measurements were obtained by the method described also in Martin Bland's presentation. So if you want to check, you basically run an automatic script which is searching for the perpendicular slice to the contact, the three-phase contact line, and this is where it determines then the contact angle. So you see here the water wet example. So this is not from this study. This is from Alessio Scanziani. And here the results of the contact angle distribution obtained from our flooded experiment. And you see that it still looks pretty water wet. And this is consistent with the images which I've shown before. But when you look at the centrifuge sample, you see here it's only indicated here with minimum, median, and maximum. You see some water wet, but most of it is actually in the oil wet domain. The reason why I displayed it here is very simple. It was actually so oil wetting, so the coverage of the oil film was so continuous that it was hardly to determine any three-phase contact lines. Yeah? So this is why we just got 20 contact angles in total. Yeah, this is why it didn't make sense to show a distribution here. Good. So we can conclude we do not see with a micro-CT real differences when it comes to occupation, but we do see that there is a difference in contact angle between those two samples, which basically means that we need to look at the smaller scale. Now, before I jump to the smaller scale, I hope the video starts. Yes, it does. I would like to emphasize that this isn't something without any relevance. So here we see a mix with the flow dynamics, which we observed actually during the mixed wet experiment at the Pauschera Institute in the synchrotron. And you see that there is a continuous change in occupation between the oil and the water. So you see here the oil in red changing. Show it again. Yeah, so you see that the occupation is continuously changing in the mixed wet case. In water wet scenarios, so I just have here one particular spot shown. The reason is in water-wet scenarios, you just see water displacing the oil. You do not see this large events happening if you just do water flood experiment. And so you see very small changes, basically fluctuations of the fluid-fluid interface, but you don't see this major changes in occupation as you see it in here. Yeah. So this difference in wetting really makes also a difference in the porosity flow dynamics. Good. So let's go now to the smaller scale and to check what is happening at the smallest at the smaller scale, where the difference comes from between those two experiments. So we investigated this using atomic force microscopy. For atomic force microscopy, you use a cantilever, which you see here. On the other side, so towards the rock, there is an atomic sharp tip, which you use to raster scan the surface. You monitor the position of the cantilever with a laser, and as you raster scan, you can use this to create a topographical image, as you see here, but also to measure force distance relationships, which I will show to you later. So here you see an example of this Ketten surface, and this is what we use to run some simulations. And basically, we used a model from aftermarket, a sphere fitting model, which is providing you the relationship between the capillary pressure and surface coverage. Yeah? So you see, we basically get smaller and smaller with the spheres as the capillary pressure increases. And in this video, so we go this way. And in this video, you're going to see how much of the surface gets then exposed to the oil. Yeah. So you see at the beginning, so we start basically here, most of it is covered with water. And as we increase capillary pressure, then more and more of the surface gets exposed to the oil. So the end of the video is basically here. Yeah. So when the water coverage is reduced and we have more and more oil being in contact with the surface, the oil alters the wetting properties of the surface and changes the wetting from water wet to oil wet. And this is basically what we then see at the micro-CT images. We also run some AFM experiments to visualize the water films. So this is a test experiment conducted on a calcite surface, which was analyzed by George Savulescu. And basically you see here, this is the calcite surface, and you see here, this is the adhesion image. This is giving you the, so when the tip moves to the surface, it crosses the fluid-fluid interface. This is what's happened here. And then the cantilever is drawn towards the surface. This is why you see a deflection up to the point where you are in contact with the surface here, where the cantilever starts bending in the opposite side. The adhesion is something which becomes apparent here. So this point here, this minimum, is basically what is displayed in this figure. And what happens is, as you retract the tip, the capillary, the fluid-fluid interface, the capillary forces of the fluid-fluid interface will keep pulling the tip down until you reach sufficient distance for it to snap off. Yeah. So this is causing this hysteresis here. Now you can use this exact point here. So this is from here, to reconstruct the droplets which you see on the calcite surface. Yeah, so you see here, this is with this point here. G is further down. You see that the fluid-fluid interface is much lower, and when you get outside of the drop, you don't see any fluid-fluid film anymore. And if you do this for all the force distance curves measured along this droplet, you actually can reconstruct this fluid droplet. And here you see the fluid distribution of two rocks initialized with different capillary pressure, one with low capillary pressure, one with high capillary pressure. for an Esteladis rock sample, and you see indeed that the coverage significantly changes. So basically, the statement is when you look at capillary pressure saturation relationships, you basically miss the effect of fluid-fluid interfaces. Yeah, so you may have just little changes in saturation, but you still may have huge changes in surface coverage. And this is why it's so important to actually look also at the sub-pore scale to see what is happening. So in conclusion, yeah, vertability is a multi-scale property. Surface roughness impacts the vertability of rock and oil brine system by facilitating fluid films, and the small-scale vertability pattern impact the pore-scale flow regimes and also the core-scale responses which we observe. Yeah, so we really need to consider all the effects across the length scales to predict what is happening at the core scale. Now, before I finish, I actually have a few more comments. Yeah. So, what are the next steps? We know that it is relevant, but how do we assess that? Yeah. Now, obviously, atomic force microscopy is limited in size. We can measure up to 100 times 100 micrometers in principle, but in practice, the largest image I ever got was 50 times 50 micrometers. Now we see the roughness is converging on this length scale, but this is only for the Ketten rock, which in origin is also rather homogeneous. So the origin of the Ketten also implies a more homogeneous structure. When we look at a different rock, so this is Bandera brown sandstone imaged by Sherifati Sufarufai, then you see that this may look quite different. She actually obtained only 5 micrometer images. And you see that there are minerals. So here you see one mineral A and here mineral B, which are as big as the whole image. Yeah. Now, yeah, so this is the height map, but you actually can look also at the other properties measured, like stiffness and adhesion, and this can be used to characterize the difference in mineralogy. So we are not really representative with AFM, but we started to look into another method, which is inverse gas chromatography. And inverse gas chromatograph really works like, yeah, the inverse of the chromatograph. In a gas chromatograph, you have a sample, you have a standard analytical column with which you probe the sample gas. So you have a mixed gas from which you don't know the components. You inject it into your standard analytical column, and this separates the gases. So you get different retention times with which you can then determine what kind of gases you injected. In the inverse gas chromatograph, you use a standard analytical gas and you have a sample medium. And the variations which you observe in the sample, they cause a difference in retention. And this is what you can then use to determine properties of the porous medium. The types of measurements which you can do is to determine surface area. And you can do measure the dispersive surface energies and acid-base surface energies by injecting different kinds of agents. Now, the nice thing about it is that you can do this at different humidity. And so you can introduce water, and due to capillary condensation, this would link to different surface coverages with change in humidity. And these are the surface energies which we measured and at different relative humidity. And you actually see that the relative at 0, you have a lower surface energy. In 10%, you have a higher surface relative, 10% relative humidity, you have a higher surface energy, which drops down again when you have 40% relative humidity. These are measurements from the Bandera brown sandstone, which we showed you before. And yeah, basically we can we assume that this changes in surface energy with relative humidity comes from the different minerals exposed to the gas at presence of the different liquids. Yeah. So this is, of course, an interesting technique, not only to assess vertability, so for multiphase flow phenomena, but for reactive transport, this might also be quite interesting, where the amount of surfaces of a specific mineral exposed to the liquid determine how many reactions you have happen, which then, of course, have, again, other mechanisms at the sub-pore scale and pore scale, which change the properties which you observe at the full scale. Now, and with this, I would like to thank you for your attention and again acknowledge my collaborators throughout, and also my industrial partners and DPNL and WO, which is going to fund the research which I just showed to you on the IGC. Thank you very much. And
thank you very much. Yes, thanks a lot for this very interesting, complex system characterization at pore scale, across the scale, by the way, not just pore, but it's good. We have questions already posted, but we expect also more to come, because this is a topic that I am on daily basis busy with as well, to characterize contact angle, capillary, and relative permeability functions. I would like to squeeze a question before I give the floor to Sebastian, and then expect him to be back to me again, because we have plenty of questions to discuss about this. It looked like that from your analysis also, looking at the same process of vertability and capillary pressure and relative permeability across the scale is crucial, not advantageous. And we try to think that a kind of a homogeneous mineral flat plate with a droplet and would give us one contact angle, one type of vertability, is all about porous media flow as well. I'd like to have your comments and share your experience with us about how crucial it is to do that for other systems, like especially hydrogen, CO2, and other fluids, that we can't really just rely on core flood-based experiments and say that's our relative permeability and capillary pressure curve. How off we will be if we only focus on one scale.
I think that we need to have in mind all the different length scales. I mean, of course, the different porous materials will have different properties, which may make one or the other length scale more important than the other. Yeah. So, for instance, if you have a very flat surface, internal surface, you may not have this large impact of roughness. Yeah. So this is certainly material dependent on where you have which effect happening, but certainly you need to consider all the effects across all the different length scales to really be able to determine what will happen.
Right. And before Sebastian mutes me, how would you make sure that you reach to a steady state situation here as well? Because there might be that you still have dynamic system and not really reach to some sort of a,
Yeah. So if you want to make experiments comparable, yeah, often indeed experiments are only run through flooding, so you don't control capillary pressure in this case. The way to control capillary pressure is through centrifugation. There you can be certain that you have a particular surface coverage, or as stated with the IVC, when you control humidity and a particular capillary condensation would also happen homogeneously across the samples. All right. Mm-hmm. So in this case, when the dynamics are less important, or you have at least a control on the capillary pressure, which we see is controlling also the amount of invasion which you get into the surface structure.
Okay. And lastly, if you have a heterogeneous system, even in the lab scale, would you decompose it into several homogeneous pieces and characterize, or you think also it's advantageous to have a heterogeneous sample also in place? For
the multiphase flow, so at the scale, I think, so I mean, it depends on at which length scale you have the heterogeneity, right? But certainly so from in a rock where you have different minerals, you would need to look also at the larger scale heterogeneity to determine the post-scale flow behavior. So it wouldn't be sufficient to just look at the smaller scale.
Okay.
The way it's the heterogeneity, so if you have different, the way it's distributed, it also matters.
Because we had also earlier, Sally Benson also presented her results for CO2 in heterogeneous settings, and I noticed that they also aim to sometimes also look into the heterogeneity in the lab too, and not just characterizing homogeneous sets of different characteristics and then expect that model would do the rest for us. Okay, excellent. Thanks a lot. So Sebastian is now going to chair the discussion session. Thanks a lot, Sebastian, for letting me ask some questions.
My pleasure, Hadi. Thank you, Maja, for a very nice talk. And I should point out before we start with the questions I think this is our first speaker who brought her own fan club. So you have your PMTTT team cheering on for you. We'll see what our next speakers, if they can also come with their own fan clubs and cheerleaders to support them. Not that you need it. It was a great talk. Thank you very much. So first question is by Yuang, and similar to what Hadi asked, so thank you for the great talk. How can we study hysteresis behavior in PC curves for CO2 brine systems? So how easy, we talked about the heterogeneity, the rock surface. How do we do, if we go to different fluid systems, how difficult would it be to adapt your studies to them?
I mean, there are different processes, of course, which we need to consider. I mentioned at the very end that there are dissolution and precipitation processes, which are also playing a role. So you change the structure at the same time as you do multiphase flow. So this is certainly complex. I would suggest to separate these two processes at the beginning to see what is the effect of one compared to the effect of the other. The hysteresis, assuming the constant structure. So in PC, I guess it has a component of hysteresis of a contact angle, and it has a on the surface level, and it has a component with trapping, of course, at the larger post-scale level. It is an interesting subject. I would consider to check out both length scales. I think Sam Crever has presented before some of the relationships between surface coverage and how it changes with saturation from a post-scale perspective. I think this is how you could link it up. I hope this answers the question.
Yeah, and absolutely. And since it triggered also the question that I asked, Sebastian, please do feel free to mute me, by the way.
No.
With CO2, because we are busy in the lab and our colleagues are also, we have additional challenge that CO2 dissolves into brine. And it's that you have a bubble of CO2, it disappears because it just dissolves. So how could you somehow make sure that you get this? And if you have even a bubble of CO2 in a captive bubble cell system, you see that over time the bubble disappears. And then you have contact angle differences through time because you have different volumes. And we have observed that for hydrogen as well. It's quite challenging to see if you are working with difficult fluids, how would you make sure that your system has reached to some sort of equilibrium to study that? So would you do the same thing with CO2 without worrying that you are getting some CO2 being dissolved into the brine as you are having your, because the time scale is important as well as length scale in the multi-scale process.
Are you asking about how to do this with a micro-CT, or are you asking about how to do
in
this
general, in the time, if you have different size of the sample and then your experiments would take different time scales, then some other physics that may not be relevant for very fast experiments may not be also relevant for. So how would you add the time characterization into this space characterization of the Vertability?
Yeah. So for micro-CT, you can run, but it's for synchrotron experiments, and with synchrotron experiments for fast phenomena, and you can also do measurements on the long axis, right? So you can do first one scan and then after some time a second scan, trying to minimize parameters which are potentially changing, to really emphasize the effect which you are looking at. As for the AFM experiment, we haven't done any dynamics yet. So I think it will be very interesting to look into some of the processes with the AFM, because of course the effects which take long time at the larger scales are rather short at the smallest scales, right? So for instance, like film swelling, dissolution, and precipitation, you see the onset already very early on. And in principle, I mean, it depends on the AFM and it depends on how fast you can do the scans. But in principle, you can also keep monitoring on what is happening along your surface in the rock with the AFM. But then, of course, it depends on the specific conditions. So for CO2, you would also want to control the pressure around it. There are very few devices which are able to do that.
Yeah, thanks very much. Yeah, thank you.
Okay, I'm going to hand over to some questions from the audience. We have a few questions from Soren, or 2 questions from Soren. There's a multi-part question, so I start out. Yeah, Soren says, well done, Maja. I have a question related to slide 6. Porous, it's actually similar to what Hardy asked and related to Hardy's questions. Porous media flows are usually slow, where for measurements, the sample is placed in the centrifuge. Wouldn't this accelerate the flow and additional effects appear? I think at dynamics or hysteretic contact angles impacting Darcy scale models.
I just needed to check what slide 6 was. I need to find you back now. I see you. Good. Yeah. So the question was related to 6 about the flow dynamics happening during the centrifugation, right?
Yes. Yeah.
Yeah. So we didn't observe the processes occurring during the centrifugation. We only looked at the rock at the very end. Of course, you have end effects. So this is something we looked into. So when we assessed with our AFM what is happening at we were in our simulations, we were checking out what is happening at the top of the sample compared to what is happening at the bottom of the sample in terms of regarding the fluids, films, and the thickness and the distribution. For our samples, the end effects were smaller than the end states of the fluid film configuration. So the dynamic effects, so the dynamic effects certainly didn't, are unlikely to have affected the results. Also, the end effects in the sample shouldn't have.
A follow-up question from Soren is, I'm going to bring this up, is continuing, can we quantify the impact of the pore wall roughness on models at the Darcy scale?
The problem, as I mentioned, is that we do not know whether what we measure is representative. So we cannot at the moment. We are looking into it. We hope that with the IGC, we actually may make a step towards that goal.
Okay. I'm going to squeeze in there's 2 questions of my own here. And you did some works on Caton limestone, and having spoken to sort of carbonate petrophysicists in the past, carbonate sedimentologists in the past a lot, there appears to be evidence that depending on actually what crystals you form, the type of calcite crystals that form in a carbonate, they influence how the wetting behavior in some of the big Middle Eastern oil formations, for example. So is that something, I'm just curious to hear your view. You mentioned that we're not representative yet, but do you think that the actual form that the calcite crystal could have, that this is going to impact wetting behavior? So even if we know it's purely calcite dominated rock, we're still quite a ways away from linking the Darcy pore scale to the Darcy scale.
I would actually like for this question to put up this one slide again. Just need to direct it. So this is the Bandera brown sandstone. What you see here, so this mineral here, this is actually clay. And what you see that it comes with a very specific orientation. We actually have observed that the adhesion is different at the edges of the clay compared to the flat surface of the clay. And so this is in the paper which is listed here. So absolutely the orientation of the mineral matter. So it's not even just the shape; it's really the orientation of how the minerals are deposited in the sample, which may make a difference. Yeah. So this the structure which is exposed to the interior does matter.
Is that how the crystal is actually formed? Now, the questions coming through from the audience, who actually, so far, the questions I had as well. So I'm going to hand over to the audience again. And we're all around related to the modeling. So Yuang asks, thank you. Have you performed any comparisons between experiments and simulations to see if the Darcy scale models, that is continuous, are capable of predicting physical observations in terms of macroscopic properties, for example, saturation profiles?
So the question is whether the Darcy scale experiments were further extended to make statements beyond what was presented. I guess.
So I read the question as, have you run any simulations to actually see if your pore scale models, your pore scale simulations could recover the processes that you observed at the multi-scale imaging, and what this means then for macroscopic properties, so relative permeability curves, but also the saturation profiles that you have visualized and displacement processes.
Yeah, so the modeling done here is really limited to the fluid coverage, the surface coverage by the liquid, so the static simple sphere fitting model. We haven't looked into further models and whether this will be sufficient really to make the link across length scales.
Okay. And Leila has a thank you, and Leila has a similar question. Just thank you for the great talk. I guess we know what the can estimate what the answer is going to be now. She wonders, have you done any sensitivity analysis with modeling to identify variations at pore scale changes or field scale predictions?
Yeah. So as I stated, it's unlikely that we are representative with the system, so we didn't dig into that. We were trying to find methods where we can determine these properties on a larger scale. This is at least the next step for us.
So I'm going to sorry, go ahead. Yeah.
Just check to which extent the data which we provide is narrowing down sufficiently to make already some first guesses about what will happen.
Even if you would have representative data, do you think that the current pore scale modeling, doesn't matter if it's pore network model or lattice Boltzmann or volume fluid type methods, are they fit for purpose? Do we miss something in the conceptual models to actually deal with the data that you're gathering, or are the models good enough?
Yeah, so basically we are proposing to obtain this capillary pressure surface coverage relationships, potentially supplemented by distributions of surface energies. So meaning that particular minerals are exposed to a specific extent at a specific capillary pressure. This will give some limiting conditions, but it's not like we could reconstruct a 3D model out of it. So indeed, the current modeling wouldn't be able to use the data which we provide as such. It will require some further thinking about how to implement. So from this data, of course, surface roughness and changes in principal contact angles, and in principle you could just use the idea of the contact. You can also keep moving on the idea of the contact angle. So basically, instead trying to converge convert this expression of the wetting state from a molecular perspective into a contact angle, which you then can implement in all the models which are currently available from DNS to PNM. Yeah, but I mean, we know from the larger scale that the heterogeneity in wetting also matters. So I feel just converting it all into one contact angle wouldn't do.
Yeah, definitely.
At least for most cases, maybe for some.
We have, I think, one sort of looks like at the moment final question. It's a more technical question. Said is also thanking you for the nice presentation. He wonders, how do you control the rock aging process by time just after flooding, or the centrifuging experiments, and the possible delay for the CT scanning? Or have you aged your rocks at all?
Yes. So the first experiment which I showed, the one with the amode test, indeed we didn't aim for aging. You may have noticed that. So we stated here it was at 40 degrees Celsius for 12 hours. This was basically the centrifugation time. Mm-hmm. Yeah. We just because we observed this was quite over, and we felt that for the fact that we haven't aged it, it was actually quite a lot. We just for this reason we treated the small samples the same way. So we put it basically into we injected the oil, put it into an oven at 40 degrees for 12 hours to see how this changes. Yeah. So of course, yeah, whether an hour or more. So I think it's unlikely that an hour or more would have made a difference, but of course this option is possible for the second crude. But of course, again, also you cannot compare crude A with crude B because they are different. Yeah. So every crude may also age. The aging process may take longer. People say 4 weeks is the standard, but actually it's just a guess. Yeah. So we didn't really look after. So here in the could be we had the first aged for 7 days and the second aged for 28 days. Yeah. But this, in particular for the Ketten, the fact that the wetting is different, this has been something which was reported also in other studies. So this is not the first study which is showing that the Ketten. So for some time actually people believe that Ketten cannot be aged. Yeah, because for whatever reason, so they wouldn't know the reason. And this study shows why it can age, or why it cannot age in specific conditions. So other crude oils have shown also that they wouldn't alter the surface, they wouldn't alter the Ketten rock, while they would alter Estelares, which are both calcite, predominantly made of calcite. So you wouldn't expect chemistry to matter too much.
Okay. Thank you very much again, Maja, for a great talk, for taking all the questions, answering all the questions so diligently. And I bring up one final comment, which is from Catherine. It's brilliant as always. Thank you for the great talk. And I think Catherine, I don't know if she's part of your fan club or not, speaking for all of us, for the entire audience. So thank you very much for joining us, for providing the time, and really interesting talk that just shows how much more research there is to be done to unravel how Vertability, microscopic molecular effects impact large-scale reservoir behavior. So thank you very much, Maja, and over to you, Hadi, for some final words.
Yes, thanks very much. Also, we recognize with Sebastian that today is our anniversary. Maja was
2 weeks late for the anniversary.
Yeah, but with academics brains that we have, it's great that we remember that Maja was our 52nd speaker. So 52 talks through all these years. Month. So it's just first year anniversary. We look forward for many more years and many more science channel with no borders, with no privilege of attending a conference or any school, a specific one. We aim with Sebastian to keep going more energetic, more geoscientific, as time goes by. And with that, I'd like to also take the chance to thanks very much all the friends, Stefan, Andreas Jackson, everybody. I can't really name all the names in here, but it's great to see you all, and many of you who stay and attend through many of these events that we have hosted so far. The channel will stay active for years to come, by the way. And you know all that Sebastian and I have agreed, hopefully we keep it, that in our retirement, after that, we will give a webinar ourselves in this channel. So that's already a good motivation for us to keep going, by the way. Martin, great to hearing from you. Wijtha as well. Everybody, Anne is here, Wiley and others. I'm sorry, I can't really read all the names, but thank you very much for being here. Rasul, you as well. So I'd like to also end with the announcement of our next week's speaker. We are going to host Simeon Agada, Dr. Simeon Agada from the UK Department for Business, Energy and Industrial Strategy. So we have a guest from the UK government to give a lecture about accelerating the energy transition. So until next week, the 53rd webinar of the Geoscience and Geoenergy. Please stay first happy, healthy, and tuned in to our channel for another geoscientific and geoenergetic talk. It's our pleasure and honor to host you every week, and I speak for Sebastian and myself both. We are really delighted and blessed with seeing you all every week and with all these great speakers and great questions that we have. Sebastian, anything to add?
No, thank you very much to our audience, to all the speakers, Maja, and the 51 other speakers. Without you, without the speakers, without the audience, it would be just Hadi and me speaking to each other at YouTube, and it would be really, really boring. So thank you, everyone, for joining us. Thank you for tuning in, and thank you to our speakers, because we really appreciate that you take the time out preparing the talk and lending us our time to help the community. So it's very much appreciated.
Maybe I can say on behalf of the Porous Media Tea Time Talks that we congratulate you very much for the great success of your platform and for all the efforts which you put into this. I think we all enjoyed it the last year to watch all the talks. Thank you very much for organizing.
Our pleasure.
Our pleasure.
See you all next week then.
Yes. Accelerating the energy transition next week. Please stay tuned in.
Bye-bye. Bye, everyone.
Bye, everyone.